So far, we have learned the arithmetic operation of different number systems. Now let us concentrate on binary system, as in computer systems, all the numbers will be converted in binary system for processing. We will see this issue later on in our later lectures. Today we will start with signed numbers in binary system. Now the computers must be able to handle both positive and negative numbers. A signed binary number consists of both sign and magnitude information. The sign indicates whether a number is positive or negative, and the magnitude is the value of the number. There are three forms in which signed integer numbers can be represented in binary. Number one is ones complement, that we learned as r minus ones complement. For binary system, this is ones complement. Another is twos complement, and third one is sign magnitude. We learned about ones complement and twos complement in our previous lectures, and these are the representation of negative number of any positive number, because when we take ones complement of any number, by adding that number with another number, we get the subtracted value. So we can say in ones complement or twos complement form, a negative number is the ones complement of the corresponding positive number. So if we take ones complement of any positive number, we'll get the negative representation of that number. Or if we take twos complement of any number, we'll get the negative representation of that number. That's why if we add that value with another number, that gives us the subtracted value. Now let us start our discussion on sign magnitude or sign bit. In this system, the leftmost bit in a signed binary number is the sign bit, which tells you whether the number is positive or negative. For example, suppose we are writing the corresponding binary value of 6, that is 110. If we use 3 bit for representing any number, then there will be one extra bit at the leftmost. This is the extra bit. If this bit is 0, this indicates a positive number, and if this bit is 1, then it indicates a negative number. If we want to represent -6 in decimal number system, that is converted to binary number system, the value of 6 is written as 110 in binary system, and the leftmost bit that will represent the sign bit, if it is 1, which will say that whether the number is plus or minus. 1 represents the negative value. So this is the sign bit. So this is the representation of +6, this is the representation of -6, and this is 4-bit signed binary number. Let us see another example. For 8-bit signed binary number, if we want to represent +25 using signed binary number, here the 7-bit will be used to represent the magnitude, and one remaining bit, leftmost bit, will be used to represent the sign bit. So the corresponding number of 25 decimal in binary is 11001. So we have used 1, 2, 3, 4, 5 bits. We need to have 8 bit, as it is exclusively mentioned that it is 8 bit signed binary number. So 1, 2, 3, 4, 5, 6, 7 will be used as our data bit, and the leftmost bit will be used as our signed bit, as it is positive, so this will be 0. Again, in order to represent -25 in binary, the number will be same, and we need to make it 8, and the leftmost bit will be 1, and this represents the number is negative. So we have 25, this represents the magnitude, and the leftmost bit represents the sign. Next, we'll start a new topic, that is digital codes. Using digital codes, a number can be represented uniquely by any binary combinations. That binary combination is called a code. Many specialized codes are used in digital system. First of all, we'll learn about BCD codes. BCD, that stands for binary coded decimal. That means decimal number will be represented using binary codes. So let's discuss this topic. Binary coded decimal is a way to express each decimal digits with a binary code. We have 10 decimal digits. If we write those decimal digits, they are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 symbols used in decimal digits. Now, in order to represent each digit using binary system, how many minimum number of bits are required? We know using 3 bits, we can represent 8 symbols. That means if we have 3-bit binary, then that will give us 2 to the power 3 equal to 8. So we can represent 8 distinct symbols. Here we have 10 symbols. In order to represent 10 symbols, we need 4-bit binary. But using 4-bit binary, we can represent 16 symbols. But for decimal system, we have 10 symbols. And that 10 symbols will be represented by 4-bit binary numbers. And there will be 6 unused states, which I'm going to show you later. So let's see how these are coded. This is BCD, binary coded decimal. Here 0 will be represented by 4 binary bits, as we have come to a conclusion that we need to use 4 bits. So there will be 4 binary bits, 0, 0, 0, 0. And 1 will be represented by using 4 binary bits, which can be written as 0, 0, 0, 1. And 2, 0, 0, 1, 0. 3, 0, 0, 1, 1. 4, 0, 1, 0, 0. 5, 0, 1, 0, 1. 6, 0, 1, 1, 0. 7, 0, 1, 1, 1. 8, 1, 0, 0, 0. And 9, 1, 0, 0, 1. We stop here. So these are the coding. 9 is coded by 1001. 2 is coded by 0010. So how to represent any decimal number using BCD code? Suppose if we want to represent 30 decimal in BCD, what is the value in BCD? This is how we represent. We will segmentize each digit. Each digit will be represented by each corresponding code. Suppose we have 1 and 3. 3 can be represented by 0, 0, 1, 1. And 1 can be represented by using BCD 0, 0, 0, 1. So we have 4 bits in each segment, and in another segment another 4 bit. So this is the binary coded 0, 0, 0, 1, 0, 0, 1, 1. This is the BCD code of 13 decimal value. Here we can see out of 16 combinations, we are using only 10 combinations. There are some unused combinations. Those are 1010, 1011, 1100, 1101, 1110, and finally 1111. These are the unused combinations for BCD codes. And these unused combinations are named as invalid codes. Invalid BCD codes in 8421 BCD. What is 8421 BCD? Let us discuss about that. The BCD codes for 10 decimal symbols that were shown in the previous page are named as 8421 BCD. The designation 8421 indicates the binary weights of the 4 bits. The binary weights are 2 to the power 3, this is the fourth bit, 2 to the power 2, this is the third bit, 2 to the power 1, this is the second bit, and 2 to the power 0, this is the first bit. First bit means LSB, least significant bit, and fourth bit is the most significant bit for 4-bit binary system. Now for any number, for example this number, if we multiply each bit with the corresponding weight, 0 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0, that will give us the value 3. And we can see this BCD has corresponding decimal value of 3. Again, if we see another example, for example, for this 0 into 2 to the power 3, we have 0, 1, 1, 1. 0 into 2 to the power 3 plus 1 into 2 square plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. That will return us 7. 2 to the power 2 is 4 plus 2, 6 plus 1, that will give us 7. And that is why this type of coding is sometimes called weighted coding. Weighted code. And as I told you earlier, in 8421 BCD system, the invalid BCDs are 1010, 1010, 1011, 1100, 1101, 1110, and finally 1111. These are invalid BCD for 8421 BCD code. We may have another weighted coding, that is 2421 BCD code. Again, this 2421 indicates the binary weights of 4 bits. Here the codes are designated in this format. You have decimal number and 2421 BCD. These are the 10 symbols for decimal number system. 0 is represented by 0000. This is the BCD code in 2421 system. 1 is represented by 0001. 2 is represented by 0010. 3 is represented by 0011. 4 is represented by 0100. Up to this much, the coding is same as 8421 system. Now, how to get the remaining BCD codes? This follows a certain rule. 9 will be the ones complement of corresponding BCD code of 0. So if we take ones complement of 0000, we'll get 1111, and that will represent 9 in 2421 BCD code. I'll show you the values using the weights. Let's see what is the corresponding value of 8. 8 will be the ones complement of 1. Ones complement of 1 is 1110. 7 will be the ones complement of corresponding BCD code of 2. We have 0010, so we should have 1101. And 6 will have a value that is the ones complement of 3, 1100. And 5 will have the corresponding ones complement of 4, 1011. Now you can see if we make a segment here, that means after 4 before 5, we can see we are getting the reflection of every bit of the corresponding numbers. For example, 9 is the reflection of 0. That means we are getting 9 by taking ones complement of 0, and we are getting 0 by taking ones complement of 9. Again, 8 is the reflection of 1. We are getting the corresponding 2421 BCD code by taking ones complement of 1, and we are getting 2421 BCD code of 1 by taking ones complement of 8. In this way, we are getting a reflection between this portion and this portion. That's why 2421 BCD codes are sometimes called reflective codes. Reflective codes. and we can verify the weights. Suppose for 9 we are getting 1 1 1 1, 1 into 2 plus 1 into 4 plus 1 into 2 plus 1 into 1. That will return us 2 plus 4 6 7 8 9. These 2 4 2 1 are the weights. Let's check another number. We have 1 1 0 0. 1 into 2 plus 1 into 4 plus 0 into 2 plus 0 into 1. That will give us a value 6, which is the corresponding value of 6. I hope it is clear to all of you. Well, there are over 8,000 ways that you can choose 10 elements from 16 binary numbers of 4 bits, but a few are useful. Here I have shown you 8421 BCD code and 2421 BCD code. We may have another type of BCD code, that is 84 minus 2 minus 1. This 84 minus 2 minus 1 are the weights. If we represent each decimal digit by 84 minus 2 minus 1 system, then the coding will look like this. You do not have to memorize all these codings, but you need to understand how these codings are extracted. Next, we'll see another type of coding, that is XS3 coding. The XS3 codings are obtained from 8421 code by adding 3. So this is obtained from 8421, this BCD code, by adding 3. That means 0011. This is the corresponding binary value of 3 in 4-bit. So if I write the XS3 code for each decimal number, for 0, if we add 3 with this 8421 code, I'll get 0011. So this is the corresponding XS3 code of 0. Then for 1, 0, 1, 0, 0. After adding 3 with this BCD, we'll get 0, 1, 0, 0. In this way, we can extract all the numbers in XS3 code system. Next 1 0 0 0, then 1 0 0 1. So these are the XS3 code of corresponding decimal numbers. Now, if you are asked to find the XS3 code of 98 decimal, then you write the corresponding XS3 code of 8, which is 1011, and for 9, 1100. So this is the XS3 code of corresponding 98 decimal. Remember, this is not binary conversion, this is code conversion. Do not mix up, not mix up conversion with coding. Two different things, conversion and coding. Suppose for binary conversion, a number will be converted to binary number. For coding, a number will be coded with binary digits. For example, 13, which is in decimal, the corresponding binary value is 1101. This is conversion, remember. This is conversion, not coding. And the BCD value of 13 decimal is, you need to write the corresponding BCD value in 8421 system, for example. So it will be 0011, and for 1, 0001. This is also expressed in binary. This was expressed in binary. This is also expressed in binary, but this is not conversion. We did not convert this decimal to binary. Rather, this is coding. We coded 13 in 8421 BCD system. Always remember the difference between conversion and coding. This is an important portion. Next, we will discuss on another type of coding, that is the gray code. The gray code is unweighted code, that is, there is no specific weights assigned to the bit positions. So we can write the gray code is a unweighted code. The important feature of the gray code is that it exhibits only a single bit change from one code word to the next in sequence. Let me write the important feature. So from one bit to another next sequence bit will have only one single bit change. Let me show you an example. Suppose we have 2-bit numbers. So using 2 bits, we can represent 4 distinct symbols. If the first digit is represented by 0, 0, as it's having only 2 bit per digit, then next digit will be 0, 1. We can see from here to here we are having only one bit change, one single bit change. This 0 becomes 1. The next number in binary sequence is 1, 0. We can see we are having 2-bit change. This 0 becomes 1 and this 1 becomes 0. So we are experiencing 2-bit change. And the next number will be 1, 1. Here we are experiencing only 1-bit change. This 1 remains same. This 0 becomes 1. But if we want to write the same sequence in gray code, then the first number will be 0, 0. Then the next number will be 0, 1. We are having only one change. This 0 remains same and this 0 becomes 1. The next number will be 1, 1. This 1 remains same. This 0 becomes 1. So only one change is occurring here. Then the next number will be 1, 0. This 1 becomes 0. This 1 remains same. So only one change is occurring here. So this is the difference between binary and gray code. This is binary. This is gray, which is expressed by binary bits. Now let us see the binary sequence and the gray sequence for 3-bit case. For 3-bit case, the binary values are 0, 0, 0, 0, 0, 1, 0, 1, 0 in this way proceeded. So if we write the corresponding decimal value, here it's 0, it's 1, it's 2, it's 3, it's 4, 5, 6, 7. Using 3-bit, we can write up to 7, then again the next number will be 0. We can see while going from 0, 0, 0 to 0, 0, 1, there is only one change. This 0 becomes 1. From 0, 0, 1 to 0, 1, 0, how many changes are there? There are 2 changes. 1 becomes 0, this 0 becomes 1. That's why it is written 2. We have 2-bit change. From here to here, we have 1-bit change. From 3 to 4, we have 3-bit change. This 1 becomes 0, this 1 becomes 0, this 0 becomes 1. So we have 3-bit change. In this way, we can extract the bit changes from one sequence to another sequence. Now, as I told you earlier, the main feature of gray code is that there will be only one change to the corresponding sequence. So here, if we write in this format, after 001, if we write 011, we will have only one single bit change. Then from 011 to 010, one single bit change. From 010, the next number will be 110. We can see we are having only one single bit change, that is this 0 becomes 1. In this way, we can write the corresponding gray code. Now, how can we get the corresponding gray code from a binary code? Let us see the procedure. The conversion of binary to gray code is quite easy. Suppose we want to convert this binary number 1, 0, 1, 1, 0. This is a binary number. We want to find the corresponding gray code for this binary number. The most significant bit, leftmost bit in the binary code, will be the same as the gray code. So this will remain same. We'll write 1 here, the most significant bit. While going from left to right, add each adjacent pair of binary code bits to get the next gray code bit. When you will get carries, discard those carries. You don't have to consider the carries. For example, 1 plus 0. 1 plus 0 will go from left to right. What is the value? 1 plus 0 will return you 1. Then 0 plus 1. We are going from left to right. What is the value? 0 plus 1 equal to 1. 1 plus 1. What is the value? 1 plus 1 is 1 0. We need to write 0 here, discard the carry. We don't have to consider the carry. Then 1 plus 0. That will give us 1. Now this is the gray code of this binary number 10110. Now let us see another example. Suppose we want to convert this number 1110. This is a binary number. What is the corresponding gray code? So the most significant will be written as it is. Then 1 plus 1 will give us 0, discard the carry. Then 1 plus 1 will give us 0, discard the carry. 1 plus 0 will give us 1. So this is the corresponding gray code of this binary number. We are getting binary to gray using this simple rule. Next we'll see gray to binary code conversion. Again, the procedure is simple but a bit different than this process. Let's see an example. Suppose we want to convert this gray code to binary. So 1 1 1 0 1. This is the gray code and we want to convert it back to binary code. The first thing is that the most significant bit will be written as it is. Now we need to add each generated binary code with the next gray code number. So 1 plus 1 will give us 0, discard the carry. We do not have to consider the carry. Again, this is the generated binary code. This binary code plus next gray code 0 plus 1 will give us 1. Again, 1 plus 0 will give us 1. 1 plus 1 in this format, 1 plus 1 will give us 0. So this is the corresponding binary code of this gray code. We can see we are getting exactly same value 10110 10110. In this way we convert any gray code to binary code. Let's see another example. 1 0 0 1. Suppose we want to convert this gray code to binary code. We are supposed to get this back. So write the most significant bit as it is. 1 plus 0 will give us 1. 1 plus 0 will give us 1. 1 plus 1 will give us 0. So we are getting from this gray code number to this binary number. Well, there are a good number of coding systems. Let me show you another type of coding system that is widely used to code different characters in computer system. ASCII character code. ASCII stands for American Standard Code for Information Interchange. These particular character codes use 128 characters as shown in this table. You do not have to memorize all the codes, but when you are asked to find the corresponding ASCII code for any character, you can use this table. Finally, we'll discuss on error codes. In error codes, we'll discuss on parity method for error detection. What is error? Suppose we are sending a 4-bit data 1011. These are 4-bit data. 1 means presence of voltage, 0 means absence of voltage. So after sending this data, it may happen that this 1 is distorted and becomes 0. So the signal that is received there in the receiving side 0011, And this is erroneous data because we sent 1011 and we are receiving 0011. We have 1 bit error. So we'll use parity method for error detection, and it can detect 1 bit error. Any group of bits contain either an even or an odd number of ones. A parity bit is attached to a group of bits to make the total number of ones in a group always even or always odd. And based on that, the parity method is divided into two parts. One is even parity, another is odd parity. A given system operates with even or odd parity, but not both. For instance, if a system operates with even parity, a check is made on each group of bits received to make sure the total number of ones that group is even. If there is an odd number of ones, an error has been occurred. Let me show you. Suppose we are sending 4-bit data 1011. We will be adding one extra bit at the very beginning of this bit to make the number of ones even if it is even parity. So we'll make it 1 and making the number of ones even. You can see we have 4-bit data and 1-bit parity bit. This bit is called parity bit. Now at the receiving end side, if this data is received, that means 0011, and the parity bit that is received here is 1, then we can see we are getting number of ones having odd value, which clearly shows that there is an error in one of the bits because we were supposed to get even number of ones. That's why it is even parity. For sending BCD numbers, suppose we have BCD numbers, we have 0000, that is the corresponding value of 0. The parity bit P will be 0 for even parities, even parity, because we are making the number of ones even. As we do not have 1 here, so the parity bit will be 0. If we put parity bit equal to 1, then the number of ones will be 1, which is odd. In order to make even parity, we need to consider the number of ones having even value. Now for 0001, how many ones are there? 1. To make it even parity, the parity bit that will be sent, that is 1. That will eventually make number of ones having even value. In this way, if we have the next number 0010, then 0011, 0100, 0101, 0110, 0111, 1000, 1001. Here we have written up to 9. So the parity bit for this code will be 1. Parity bit for this code will be 0. Parity bit for this code will be 1. Parity bit for this code will be 0, 0, 1, 1, 0. Again, the same thing can be done for odd parity. Odd parity. If we take the same BCD number, so let's copy it, then the parity bit here will be 1. Next, it will be 0 here. Why are we putting 0 here? Because in odd parity, our main target is to make the number of ones odd. As we are already having odd number of 1 here, so we are putting parity bit equal to 0. Eventually that will give us odd number of ones. Here we are having odd number of ones, so the parity bit will be 0. Here we are having even number of ones, so the parity bit will be 1 to make the number of ones odd. Next it will be 0 here, 1 here, 1 here, 0 here, 0 here, 1 here. I hope it's clear to all of you. Next we'll see BCD addition. BCD additions have particular importance because digital clocks, digital thermometers, digital meters, and other devices with 7-segment displays typically use BCD code to simplify the displaying of decimal numbers. Though BCD is not as efficient as straight binary for calculations, but it is particularly useful if only limited processing is required. Now we'll see the BCD addition process, how to add two BCD numbers. Step 1. Add the two BCD using the rule of binary addition. This is step 1. Step 2. If a 4-bit sum is equal or less than 9, then it's a valid BCD. I hope by now you know what is a valid BCD and invalid BCD. Whenever we say any BCD number without referring the code, for example 2421 or 8421, typically by default we consider it as 8421 BCD system. Now next, step 3. If a 4-bit sum is greater than 9, or if a carry out of the 4-bit group is generated, then the result is invalid. If we get invalid BCD in the result, then we need to add 6. Add 6, that means 0 1 1 0 with the result. That will give you a valid BCD output. Why do you need to add 6 with the output? I'll give this explanation later on. For the time being, you just keep it in your mind that whenever we'll get invalid BCD, you need to add 6 with the result. Now let's see some examples, then the idea will be very clear to all of you. Suppose we want to add these two numbers, 3 plus 4. The result will be 7. So what is the corresponding BCD of 3? That is 0 0 1 1. And what is the corresponding BCD of 4? 0 1 0 0. Now let's add these two numbers using typically binary addition process. 1 plus 0 will give you 1, 1 plus 0 will give you 1, 1 plus 0 will give you 1, and 0 plus 0 is 0. Now is this a valid BCD? This is obviously a valid BCD because this is not greater than 9. So the corresponding decimal value of 0 1 1 1 is 7. So if we add these two BCD numbers, we'll get the result equal to 7. Now let's see another example. Suppose we want to add 23 plus 15. What will be the result? I'll write the result later on. Let's convert this to BCD. What is the corresponding BCD of 3? That will be 0 0 1 1. And what is the corresponding BCD of 2? That is 0 0 1 0. We have 4 in one group and 4-bit in another group. Again, for 15, what is the corresponding BCD of 5? 5 can be written as 0 1 0 1. And the corresponding BCD of 1 is 0 0 0 1. Now add these two numbers using binary addition. 1 plus 1, that will give you 0 and 1 carry will go there. 1 plus 1 plus 0 will give you 0 and 1 carry will go there. 1 plus 1 will give you 0 and 1 carry will go there, and 1 plus 0 will give you 1. Is this a valid BCD? This is a valid BCD. So we do not have to do anything. Again, 1 plus 0, 1, 1 plus 0, 1, 0 plus 0, 0 plus 0. Is this a valid BCD? This is also a valid BCD. So both the numbers individually, they are less than 9. So if a 4-bit sum, this is one 4-bit sum, this is another 4-bit sum, is equal or less than 9, then it's a valid BCD. So these are valid BCD. So what is the corresponding value, BCD value of this number? That will give you 8. And what is the corresponding BCD value? This is 3. So the result will be 38. 38. If we add these two numbers, 5 plus 3 will give you 8 and 2 plus 1 will give you 3. Now let us see another example. Suppose we want to add 9 plus 4. What will be the result? I am coming to the result later on. Let's write the corresponding BCD of 9, that is 1001, and the corresponding BCD of 4 is 0100. Now if we add these two numbers using binary addition system, 1 plus 0 will give you 1, 0 plus 0 0, 1 plus 0 1, 1 plus 0 1. Is this a valid BCD? No, this is not valid BCD because this binary equivalent is greater than 9 decimal value. So what we need to do when we have 4-bit sum is greater than 9, then we need to add 6 with the result. So we need to add 6 with the result, then we'll get the final result. 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, and we have carry 1, 1 plus 1 plus 0 is 0 here, and there will be a carry here. So this is 4-bit group, and we have another 4-bit group. If we put 3 zeros at the beginning, so we have another 4-bit group. What is the corresponding decimal value of this BCD number? That will return you 3, and we have 1. So the result will be 1, 3, 13. And we can see 9 plus 4 equal to 13. Let us see another example. Suppose we want to add 67 plus 53. Let's write the corresponding BCD value for each number. For 7, this is 0111. For 6, this is 0110. For 3, this is 0011. And for 5, this is 0101. Now add these two numbers using binary addition system. 1 plus 1 will give you 0. 1 plus 1 plus another carry, that will return you 1, and 1 carry. 1 plus 1 will give you 0, and we have 1 carry here. That carry will come here. So is this a valid BCD? No, this is not a valid BCD. So what we need to do, we need to add 6 with this number 0110. Let's add 6 with this number. 0 plus 0, 1 plus 1 will give you 0, and 1 carry will go there. That 1 plus 1 will give you 0, and 1 carry will go there, and 1 plus 1 will give you 0, and 1 carry that will come here. This carry, as we have another digit, so this carry will be taken here. Now let's start solving for this number. 1 plus 1 will give you 0. Again, we have 1 carry here. 1 plus 1 plus 0 will give you 0. 1 carry here. 1 plus 1 plus 1 will give you 1, and another 1 carry here, and 1 carry will come here. Is this a valid BCD? No, this is not a valid BCD. So what we need to do, we need to add 6 with this number 0110, and finally we'll get 0 plus 0 will give you 0, 1 plus 0 will give you 1, 1 plus 1 will give you 0, and 1 carry will be here. 1 plus 1 will give you 0, and 1 carry will be here. So we are getting 3 sets of 4-bit number. This is one set. This carry was sent here, so we will not consider this one. We have another set, and we have third set by putting 3 zeros at the beginning. So corresponding decimal value of 4 zeros is 0. We have 2 here, and we have 1 here. So the result will be 120, 120. I hope the process is very clear to all of you. Now the question is, why do you need to add 6 when the addition is invalid BCD? Because for binary coded decimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the corresponding binary value is 0000 using 4-bit binary. 0001, and up to we have 1001, and this is binary, and the corresponding BCD is having the same value, but the next binary number is 1010, but the next BCD value is 10000. Now whenever we are getting any value that is equivalent binary value is 1010, which corresponds to 10 decimal value, we need to express it by this number. So what we need to do, we need to skip 6 steps, because we have 6 additional invalid numbers which we need to skip and come back to here with a carry 1 and this 0000 value. So that's why in order to skip that 6th step, we need to add 6. So whenever we'll get any invalid BCD that is valid in binary case, we need to skip 6 steps in order to get the next carry 1 and the corresponding BCD value. That is why we always add 6 with invalid BCD numbers. We will continue in the next lecture. Thank you.